Welcome everyone. Today we are diving into Unit 2 of Data Analytics and Visualization, which focuses entirely on statistical testing. So let me emphasize right at the start. So this is a highly critical unit for your exams. Unlike theoretical chapters, this chapter carries major numerical problems. So if you master this course steps and concepts today, you can score full marks on the numericals because they follow a strict logical template. Alright, so our main goal today is to understand the bedrock of statistical inference, that is hypothesis testing. Alright, we'll be talking about what is hypothesis testing, what is its significance, and we will talk about different types of tests, that is Z test, T test, and also talk about what are the parametric and non-parametric tests. We'll also be considering ANOVA. Alright, we'll talk about Simpson paradox, confidence interval, correlation, and causation. And there will be numericals with every statistical testing method we will be discussing. Alright, so let's, without wasting any time, quickly move forward and discuss what hypothesis testing is. So to understand hypothesis testing without getting bogged down in the math just yet, think of it as a statistical court trial. Okay, think of it as a statistical court trial. So in a criminal court, a defendant is assumed innocent until proven guilty, right? And the prosecution must gather evidence to prove guilt beyond a reasonable doubt. And if the evidence is weak, the defendant goes free, and not necessarily because they are completely innocent, but because there wasn't enough proof to convict them, right? That is how hypothesis testing works. It works exactly the same way. So we make a claim about a parameter, we gather the sample data, that is our evidence, and we reach a verdict based on the probability of that evidence occurring by the chance. So if we have enough evidence to prove, then we have claimed the population parameter, otherwise we claim the opposite. Alright, so let's understand the basic thing. So hypothesis testing compares two opposite idea about a group of people or things that uses data from small part of a group, that is the sample. Alright, so we have two opposite ideas and we have one sample. So either this would be true, either this would be true. And in order to identify which one is true, we use hypothesis testing. That is what it is called. Alright. So there are two things we need to understand. So every statistical test begin setting up two opposing statements, right? That is the hypothesis. So first we have null hypothesis, which is identified by H0 mostly. And then there is second, that is alternative hypothesis. Alright, so these are the two opposing statements. So what does null hypothesis means? Think of this as a status quo. Status quo, right? The baseline, all the innocent bystander. So this is the innocent bystander. It always claims that there is no effect, no difference, or no change. For example, if a company launches a new website design, so the null hypothesis would state that the new design is the exact same. New design has the exact same conversion rate as the old design. Alright, so we assume that H0, that null hypothesis, is true until the data proves the otherwise. Alright, so we have two opposing statements. One is the null hypothesis, that is mostly talking about, it claims that there is no effect, no difference, no change. And the alternative hypothesis, which is mostly dominated by H1, is the challenger. It's the statement you are actually trying to find evidence to support. It says that no, there is a difference. Okay, there is a difference. So null hypothesis says that there is no difference, and alternative hypothesis say that there is a difference. All right, so or we can say that there is a new method that is significantly better. So these are the two opposing statements, right? That is how it works. So when writing these numericals, when we write the alternative hypothesis for the numerical, remember that H0 always contains this equality signs, either this or this or this is what H0 always include, but H1 alternative hypothesis never include these equality signs. All right, it is a statement that is proving this one wrong, so it is just opposing. All right, so I hope you understood this concept. So we have hypothesis testing, that is testing the two ideas, two opposing statement, and those opposing statement, one is the null hypothesis and other is the alternative hypothesis, or H0 and H1. So H0, for example, the average salary of data scientist is 10 LPA. So average salary is equal to 10 LPA. So you see we have equality sign, and in this we'll just write not, that average salary is not 10 LPA. That is how you write. Okay, this is the example of how H0 and H1 works. Alright, so the very next thing we need to understand is types of testing. So depending on how you state your alternative hypothesis, your test will either be one-tailed or it will be two-tailed. So this completely changes where you look on your probability distribution chart to find your final answer. So what does these mean? So first you need to understand that we have two types, right? So two-tailed test states that this is used when you want to look for any difference, whether it is higher, all right, or it is lower. For example, if you are testing if a machine pour exactly 500 ml of soda. Okay, so your null hypothesis, your alternative hypothesis would be that the volume is not equal to 500 ml. This will be the alternative. Null would be that it is exactly 500 ml, right? So opposing would be not equal to. So you will check the critical rejection region. Where will you check it? Either it will be less than 500 ml or it will be greater than 500 ml, right? So you would see that you are checking the both ends, the lower and the higher end. That is the two-tailed test. So the rejection region is split equally on the both tails of the curve. That is the, you see over here, two-tailed test. So this is the curve and both the regions are considered in two-tailed test. And now the one-tailed would be quite understood that this is the directional hypothesis. So you only care if the outcome is specifically greater than. So in this 500 ml example, you just care that either machine is putting greater than 500 ml or not. So you are just focusing on one particular end, right? You only look at the upper right tail of the curve to check what the answer is. Alright, so missing the distinction in an exam will lead you to pick the wrong chart values. So read the question carefully. Either it says increased, either it says decreased, or it says different, right? So these are the keywords to identify, is it a one-tailed test, is it a two-tailed test. Let's quickly understand the difference between null and alternative hypothesis. So this states no relationship exists between the variable, and this is opposing this particular statement stating that there is a relationship. It assumes that there has been no effect, no change, but here we assume that there is effect. It considers the default assumption. So whatever our problem statement is, it becomes the null hypothesis, and whatever we want to have a research claim and whenever we need some evidence, that become alternative hypothesis. And the researchers try to reject this hypothesis, and researcher try to support the alternative hypothesis. And if accepted, alright, if accepted, researcher may need to reconsider their assumption, that whatever they were assuming, right? So they need to reconsider if null hypothesis become true, and if accepted, then researchers support their original claim. All right, so whatever claim they made, that is the alternative hypothesis, right? So that is why they support that. So no observable impact on the output, but if alternative hypothesis becomes true, then it impacts the output, right? So this is how these terms play a very vital role when we'll further discuss about the types of tests. So let's quickly revise what we have discussed about the one-tailed and two-tailed test. So one-tailed test is the statistical hypothesis where alternative hypothesis is one-tailed, either it is right-tailed or left-tailed. All right, so the critical regions are either on the left or on the right. So there is a or statement. But in two-tailed test, the hypothesis is on the both sides. So there is an and statement. For one-tailed, you use either less than or greater than sign, or for two-tailed, we use not equal to sign for the alternative hypothesis. And when alternative hypothesis specify a direction, then we use one-tailed test, and when there is no direction specified, then we use two-tailed test. So if there is no keyword like increased, decreased, that means we are using two-tailed because the direction is not specified, right? And if we talk about the critical region relies entirely on the right side or the left side, whereas the critical region is given by the portion of area lying in both the tails. So whenever we see a graph in this, the critical region would be around both the tails. All right, so this was about one-tailed and two-tailed test. Now let's look at the core components that you will manipulate in every single numerical problem. Okay, so think of these as a gear inside a statistical machine. First, the very most component is the test statistics. So the test statistic is a numerical value that you calculate directly from your sample data using a formula. All right, so test statistic is essentially measures exactly how far your real world sample diverges from what the null hypothesis predicted. So the bigger the number, the more suspicious we are of the null hypothesis. All right, that is what we call test statistics. So whatever the numerical value we generate from the test score, from Z score, T score, whatever we test apply, whatever the numerical value is, that is known as the test statistics. Next we have is the level of significance, and it is donated by alpha. All right, so it is a threshold proof. All right, it is a threshold. So when you see over here, yes, so this is the threshold proof, the level of significance, and it is the maximum risk you are willing to take of making a mistake. All right, so this is the borderline, and after this borderline, whatever lies is the is something which is where we reject the null hypothesis. All right, so what we do, it is a maximum risk you are willing to take of making a mistake, especially it is a type 1 error. Okay, type 1 error convicting an innocent null hypothesis. So usually the alpha is set to 0.05, all right, at 5%. So this means you only reject null hypothesis if there is less than 5% chance that your result happened by pure luck. All right, so this is the 5% where you reject it. Okay, and next we have is the critical value. So critical value is the boundary line on your distribution curve. It is dictated entirely by your alpha. So whatever the value of alpha, so this is the rejection region. All right, this is the rejection region. So this is the critical value. So it can be here, it can be here. It depends on the alpha. It depends on the significant level. All right. So this boundary mark the beginning of decision boundary and the rejection region. So this is the decision boundary, this is the rejection region, and then we have the alpha, which is 0.05. all right, and it can vary as well. So if your calculated test statistic crosses over the critical value line and land inside the rejection region, so you reject the null hypothesis and shout out that we found the significant result and we prove that alternative hypothesis is true. all right, so that is the critical value. Then we have decision boundary, like I told you right now. So decision boundary would be the specific region of probability distribution where if the rest test statistic land here, so null hypothesis is rejected. Again the same thing. all right, next we have p value. all right, so p value stands for probability value. It is probability value. It is the exact probability of getting your sample result. all right, or something even more extreme, and assuming that the null hypothesis is completely true. all right, so what does the p value states? That if the p value is less than or equal to, okay, so if it is less than or equal to the significance level, so if p value is less than equal to the significance level, it means that a result is highly unlikely to be fluke, so we reject the null hypothesis. all right, and if the p value is greater than, all right, it is greater than the null hypothesis, if it is greater than the significance level, that means the null hypothesis, the H0, it survives. So based on the p value, we define if our null hypothesis will be rejected or accepted. all right, so it is the probability value. It is the exact probability of getting your sample result. Then comes the confidence interval. Confidence interval is the dual twin of hypothesis testing. So instead of giving a single yes or no, instead of giving the single yes or no answer, it provides an estimated range of values like 90%, 95% confidence that likely contain the true population average. So if your hypothesized value under H0 falls completely outside the range, it is mathematically identical to rejecting H0 at a significance level of 0.05. So confidence interval is the range which is derived from same sample data, and it is likely to contain two true population parameter with specified level of confidence. all right, so what we do over here, we simply write that if there is 95% of confidence interval, that it would be rejected at 5%. all right, so we are 95% confident and 5% is where lies our risk. all right, next we have is degree of freedom. So finally, degree of freedom is a concept you will see in almost every numerical table, like t test, or there is chi-square test as well. So it represents the number of independent pieces of information available in your data to estimate a parameter. So look at this way, that if you have three numbers that must add up to 100, so there are three numbers and it should add up to 10. So you can choose any number you want for the first two. Let's say you choose 5 and then you choose 2, but the third number must be 3 to make the sum 10. all right, so this must be 3. This is static, and you can choose these two number and the sum should be 10. So it has no freedom, right? Therefore, for a simple sample mean calculation, your degree of freedom is always n minus 1. okay, this is the degree of freedom. So because the last piece of data is locked in a place by the sample mean we estimated. So now we have all the definitions. So degree of freedom is calculated by n minus 1. So where n stands for sample size, and we use this to identify our value. Alright. So if we talk about, you see over here, for example, we have one tail distribution and our significance level is 0.10 and degree of freedom is 14. That means sample size is 15. Degree of freedom is n minus 1. That means it is 14. Alright. And based on that, we identify what is the p value. Right. And that is what we use as over here. So we have significance value and we defined our p value, and this is the critical region, right? And you will be able to understand if we take the example clearly. Okay, so you see the significance value, this is the critical value, this is where you accept the null hypothesis, this is where you reject the null hypothesis, and this is the p value, right, which we identify. And then we get the test statistic according to the formula which we apply, and after the applying the numerical we get the answer. That answer is known as test statistic. So this is how you are able to actually calculate if there is a probability of occurring something or not occurring of something. Alright, I hope you understood these terms really well, what test statistic is, what level of significance is, and this will clear up more when you understand it by a numerical, right? So let's move forward and discuss about what are the types of errors. Okay, so you see that now that we know that we have to set up a hypothesis and choose our test, we need to talk about error margin. Alright, we need to talk about error margin because we are using sample data to make assumption about the entire population. There is always a small chance that our conclusion will be wrong. So in an exam, you are frequently asked to define type 1 and type 2 error or map out a decision matrix. So what is it? Let's look at quickly. So you look at this, that on the right side, so this side is the absolute truth. So as a data analyst, we don't actually know, right? And across the top, we have the decision verdict. So decision verdict failed to reject the null hypothesis and reject the null hypothesis. So these are the decision. And this is the reality, that null hypothesis is true and null hypothesis is false. Alright. So if in reality the null hypothesis is true and we fail to reject the null hypothesis, then we have created a correct decision, right? So here we made the correct decision. So the mathematical probability of this is 1 minus alpha. Okay, then comes the scenario B, that in reality the null hypothesis is true and we reject the null hypothesis. This is where the problem begins. It was true in reality, but we rejected it. So this leads to error, type 1 error. This is known as false positive. Alright. So we gave the wrong, we made the incorrect decision, right? So this happens when the null hypothesis is true, but we mistakenly reject it. Alright, so we conclude that there is an effect, there is a difference when there is actually was no difference. So this is equivalent to condemning an innocent person. So the innocent person didn't do anything wrong, but the court found them guilty anyway. That is the type 1 error. Okay, so remember that you control this risk yourself. So when you are choosing a significance level, like you are choosing it to be 0.05 for a numerical problem, so you are explicitly saying that I am willing to accept a 5% risk of committing the type 1 error. Okay, so you are mentioning that I am accepting the 5% risk. Okay, and then you see when null hypothesis is actually false, right, and you reject the null hypothesis. So when it is actually false and you reject the null hypothesis, then you made the correct decision, right? So this is known as statistical power, and it is defined as 1 minus beta. Alright, this is 1 minus alpha, correct decision. 1 minus beta, statistical power defined as 1 minus beta. So these are the two correct decision. But what happens if null hypothesis is actually false and you fail to reject the null hypothesis? Then you create the type 2 error that is called false negative. Alright, so actually it was false and you said no, it's true. So this is equivalent to letting a guilty person go free. So the crime was committed, right? The crime was committed. H1, H0 is false. But the evidence wasn't strong enough, so the court let them walk out. Let that guilty person go. So in data terms, your test missed the real trend or an improved business opportunity because the sample size might have been too small or the data might have been too noisy. We don't know what the reason is, but you actually missed the opportunity. That is the type 2 error. Alright. So if we dive deeper into the errors, like I told about type 1 error. So in type 1 error, what we are doing, we are condemning the innocent person. And in type 2 error, we are letting the guilty person go free. And what is the statistical power? So this brings us to the final matrix. Statistical power is 1 minus beta. It is the probability that your test will correctly reject the false null hypothesis. So in plain language, it is the strength, or we can say sensitivity of your test to successfully detect a real effect on one actually exists. So if your test has high power, for example 80%, alright, it means you have 80% chance of spotting a true difference and only 20% chance of actually missing it. So this is the type 2 error. Alright. So as a data analyst, you always want your statistical power to be as high as possible. Alright, so statistical power to be as high as possible, and you can do this by increasing the sample size. So sample size should be increased. Alright, so for the summary, you need to understand that type 1 error, we are rejecting the true null hypothesis, innocent person. And for type 2 error, what we are doing, we are failing to reject the null hypothesis, we are letting the guilty person walks away. And statistical power is correctly identifying a true effect. I hope you got this. Now that you understand the rules of the game, the hypothesis, the error rates, and the decision region, it is time to look at our very first actual statistical test, that is Z-test. Alright, so if you look at the past exam papers, you will see the numerical question are heavily drawn from this section, and the good news is that Z-test follow a fixed mathematical pattern. So once you know how to identify a Z-test problem, the calculation is straightforward. So you just need to remember the formulas and the pattern. Alright, so what is exactly Z-test? It is a parametric statistical test. Alright, parametric statistical test. What does parametric simply means? That we are making assumption about the parameters of the population distribution, especially that the data follows a symmetric bell-shaped curve. That is the parametric statistical distribution, right? So we use Z-test. We use Z-test to compare sample mean, sample mean against the known population mean, to see if there is a statistically significant difference. It relies entirely on standard normal distribution, that is known as Z distribution, right? That means that the mean is exactly 0, and standard deviation is exactly 1, like we talked about the Z score, right? So that is what on this Z test relies on. So there are 3 golden rules when to use Z-test. You need to understand that to choose a Z-test, the problem must satisfy these 3 strict criteria. So write these down because these must be your checklist. So first is the sample size. So the sample size that is defined by n should ideally be large, meaning it should be greater than 30. Sample size should always be greater than 30. Why 30? Because foundational rule in statistics called central limit theory, right? We talked about it. Theorem. So what does it say? This theorem guarantees that if your sample size is large enough, the distribution of sample mean will look normal. So if the original population data was skewed, if the problem statement states the population is already normal, then the z-test can technically be used for smaller samples too. But n is greater than 30 is your classic exam trigger, right? So the very first checklist is that whatever the sample size is given, it should be greater than 30. Okay, and next is the population deviation should be known. This is ultimate absolute deal breaker. So look closely at your text of the question. Does it give you an population standard deviation? Like, does it give you standard deviation or not? If it says that population deviation is, for example, 5, that means you can perform z-test. If it only gives you sample standard deviation, you cannot use standard z-test unless the sample size is massive. Alright, if it only gives you it only provides you a point, then it is not required, then z-test cannot be used. Then you have independent data point. So the data point must be completely independent of each other. This means if one person scores or one item measurement cannot influence the other. Alright, so data point must be completely independent. For example, testing the height of randomly selected student works, right? And testing the height of identical twin violate the independence because they are biologically related. So this is very important point, that data points should be independent of each other. Okay, so now we'll understand the z-test with a detailed example. So make sure you understand it from a exam point of view. It is very essential. Alright, so let's begin with our example. If we talk about the question, it states that there is a tech company. So the tech company claims that its old server architecture handle over 500 requests per second, and the cloud engineer optimizes the code base and runs a sample text across 35 different time windows, finding the sample mean of 515 requests per second, and the historical population standard deviation is known to be 40. So test at a 5% significance level whether the optimization significantly increased the performance. So what did you identify from these things? First of all, before writing anything down, check your triggers. Is the sample size greater than 30? Is the sample size greater than 30? Here the n is equal to 36, right? So check. Now we check if the population standard deviation known. The historical population standard deviation is 40. Yes, it is known. So this confirms that we definitely doing a z-test. And other than this, they are asking us to check if it significantly increased the performance. That means it is a one-tailed test, right? So we are just checking the one level that is increasing. Okay, now we set up the variables. The very first step of z-test is to state the hypothesis. The question explicitly asks if the optimization increased the performance. The word increase tells us that it is a one-tailed test. So let's perform null hypothesis. So very first hypothesis, null, states that the optimization made no difference. That means the mean is 500. In other words, the optimization has no difference. Now we have alternative hypothesis, which will state that increased, right? So that means mean is greater than 500, meaning performance increased, right? So we have null hypothesis which states that there is no change, and we have alternative hypothesis which means that there is increase in the performance. Now we have now we need to identify the given information. We'll list out all the variables clearly in your answer sheet, so you don't have to make any careless substitution errors. First of all, the population mean is 500. Alright, then they have given us the sample mean as well, so we'll jot down it that sample mean is 515. Then we have standard deviation as 40, sample size as 36, and we are also given the significance level of 0.05. So we have noted down all the essential information. Now let's move on to the step 3, that is finding the critical value and setting the decision boundary. So alright, because it's a right-tailed Z test and we have alpha significance value as 0.05, so we'll look at the Z table for the value that leaves 5% to the right tail. That means 95% to the left. So we have to look for value 0.09, right? 0.095, because 95% of the value is left, that is the major null hypothesis area, and the 0.05 is the area where we actually reject the null hypothesis. Alright, so for this critical value, sometimes it is given in the question paper, because we have to look at the Z table. So this is what Z table looks like. This is the Z table representation and the values for every feature. Alright, so you see over here we have 0.5, right? This is 0.5, and upon the 0.5 value we check where is 0.95. This is 0.95, and to the left this is the value which would be the critical value, this the Z critical value. So this is how we find the values. So there are all the significance levels and the critical value for that particular significance level. So for 95%, right, for 95%, and for the 0.05 significance value we have 1.6 critical value. So this is how we get our value 1.645 critical value from the Z table. So it is mostly given in the exams. If not, they provide you the Z table. Alright, then comes the decision rule. So what does the decision rule say? That if the calculated Z score, which we'll calculate here, the calculated test statistic is greater than the critical value, which is 1.65, then we reject the null hypothesis. Alright, so you see what is happening. This is the critical value 1.645, and if the Z value is greater than this, that means it falls in the rejection area, right? That is why we reject the null hypothesis and accept the alternative hypothesis, right? So let us quickly calculate the test score. So to calculate the Z test score, we have the particular formula. Alright, so the formula directly states that Z test statistic is equal to the sample mean minus the population mean upon standard deviation divided by root of number of sample. Alright, and we have all this information right over here, which we have already written down. Alright, so we'll just put on the values and then we calculate. So our Z score come out to be 2.25, right? So this is the calculated Z score. Now you know that we have a decision rule that if the calculated Z score is greater than 1.65, that means we reject the null hypothesis. So 2.25, since 2.25 is greater than 1.645, that means we reject the null hypothesis and accept the alternative hypothesis, right? So this is what we write. We make the statistical decision and we write that since the Z score is greater than the critical value, that means it fall in the rejection region. So you see, you have to draw such diagram, such graph in which you have the tailed diagram, and we have the Z critical value, and then we have the test statistics, which is 2.25. This is the calculated score, right? And it is falling on the rejection area. And we also mentioned that the alpha, that significance level is 0.05, right? And then we provide the interpretation. So guys, don't just stop here in your exam, do mention the interpretation, because this is the concluding sentence that relates back to the real world problem. So we write that there is statistically significant evidence that at 5% level to conclude that the cloud engineers optimization successfully increase the average server request beyond 5%, 500 per second, right? So it's simple as that. You state the hypothesis, extract the variable, found the boundary, and run the formula and make your verdict. So here we just rejected the null hypothesis and proved that alternative hypothesis is true. Now that we have mastered Z-test, let's talk about what happens when real world constraints hit us. In many actual data analysis scenario, and definitely in your exam question, you won't always have large sample size, right? And you almost never know the true population standard deviation. So when you find yourself in this position of higher uncertainty, Z-tests fail us, and instead we must turn to t-test. Alright, so what is a t-test? A t-test is also a parametric statistical test used to compare means, but it operates under different probability, that is known as students t distribution. Alright, so a quick bit of trivia that examiners love. It's called students tree distribution because it was developed by chemist named William Seeley Gossett, who worked for the Guinness Brewery, right? So he wasn't allowed to publish under his real name due to a trade secret. So he published it under a pen name called Student, because he couldn't use his own name because he was working under someone, right? So mathematically, if you look at the graph, this graph, right? So the t distribution looks very similar to the normal Z distribution. It is bell shaped, it is symmetric. However, it has heavier, flatter tails. Alright, so it has fatter tails. Why? Because when your sample size is smaller, or you don't know the population variance, you have extra uncertainty. So the fatter tails, right? So the critical values are pushed further out, making it slightly harder to reject the null hypothesis by pure luck. That is why it is known as students t distribution. All right. So the main thing you need to understand is that there the sample size should be smaller than 30. And the other thing is that there is standard deviation is unknown. We don't know the standard deviation, right? So this is the primary indicator. The problem will not give you a population standard deviation. Instead, it will say something that a sample of 15 items was taken, showing the sample standard deviation of 4.2. The moment you see that you are forced to use sample standard deviation as substitute for the sigma, right, your brain should immediately scream that it is a t-test. All right, so first the standard deviation is unknown, then the sample size is less than 30. You cannot rely on central limit theory to smooth the things out in the perfect normal distribution, right? So but what if the sample size is large, right? It is but the population variance is still unknown. So technically n grows larger and t distribution changes shape and blends perfectly into Z distribution. But for your exam purposes, if you are given a sample standard deviation and a small sample, it is strictly a t distribution. All right, so you focus on the sample size for now on. And then underlying population is normally distributed. So this is the another criteria in which we use the t-test. Alright, so let's look at how we actually do this. So we have another scenario over here, and in this scenario, we'll apply the t-test knowledge to a hands-on numerical. Alright, so this problem is slightly different because instead of giving you a neatly summarized sample mean, it gives you raw number, and this is a very common, this is how you actually receive your exam. Alright, so the scenario says that there is a boutique coffee roaster that claims that their bag of espresso bean contain exactly 250 grams. Okay, and a spectacle quality inspector randomly samples 10 bags and weighs them. The weight were this 10 items weight. Okay, so test at 5% significance level whether the bag are systematically underfilled or not. Alright, so this is the question. So let's look at our triggers. First of all, we are given that the sample size is 10. Alright, so n is equal to 10, which is less than 30. Alright, more importantly, we do not know the standard deviation. There was no information provided for standard deviation, and we only have the raw data for the 10 bags, right? This tells us that we have to instantly perform a t-test. So very first thing is, first of all, we need to state the hypothesis. So this is the always the beginning. So the key word in the problem is underfilled. Alright, so this means the inspector only suspect that the true weight is less than advertised. Okay, it is less than advertised. So because we are looking at the single direction, this is also a one-tailed test. I hope you are able to understand how we are doing, and it is also a left-tailed. Alright, now we are testing specifically if the bags are underfilled. So first of all, our null hypothesis means that it maintains the manufacturer's claim that the bag has 250 grams of weight, and the alternative hypothesis would be that it represents the inspector's suspicion that the weight is less than 250 grams. So these are the two hypotheses we will be testing. Now we'll compute these sample matrices from raw data. So when an exam question gives you a raw list of data points, your first order of business is calculating the basics yourself. Alright, so we'll jot down whatever information we got. First of all, sample size, which is n, denoted by n, is 10. Then we have to calculate the degree of freedom. Alright, so this means the degree of freedom would be 9, because degree of freedom is calculated by n minus 1, where n stands for sample. So we have 9 as the degree of freedom. So keep this number handy because we need it for the distribution table, right? And next we'll calculate the sample mean. So sample mean is also not given in the question. So we are adding up all the 10 weights and dividing them by the 10. So how we actually understand how mean is calculated, the basic mean calculation. So when we add all the 10 weights and divide by 10, we get our answer. Okay, so that is 247.4 grams. So this is the sample mean. Alright, and then we have the sample standard deviation. So using the sample variance formula, we will calculate the sample standard deviation. Alright, so how are we gonna do it? This is the formula for the sample standard deviation. So for every value of the sample, we will minus it by the sample population mean, square it, and then n minus 1, which is the sample minus 1, and then we put it to the root, right? So this is how we calculate the standard deviation. It comes out to be 2.119 grams in our case, right? Moving forward, we find the critical value, just like we did in the z-test. So to found our decision boundary, we go to the t-test distribution table. So let's quickly look at our t-test distribution table. So we look up the row for df is equal to 9. Alright, so this is the row and we look at the row 9th. Alright, this is the row we are looking at, 9th row, and then we will see that it is a one-tailed test and our significance level is 0.05. So one-tailed test significance level is 0.05. Okay, and this is where we are intersecting, right? So we get 1.833. Alright, so this is listed, the value listed is 1.833 and we'll consider this particular value. Alright, so since it is the left tail test, so on the left that means it is the negative, and if it is the right tail test, then we consider the positive value. So since it is a left tail test, we will be considering the negative value, that means minus 1.833. Alright, so decision rules state that if the calculated t value is less than minus 1.833, then we reject the null hypothesis, right? So meaning it sits deeper in the negative left tail, that it is lesser than minus 1.33, then we actually reject the null hypothesis. So this is the formula to calculate the t test statistic. Now we plug our custom matrices into the t-test formula. Alright, so on the numerator part, you see t is equal to sample mean and we subtracted by the population mean. Alright, so the sample mean is 247.4 minus the population mean, which is 250. And then we are dividing it by the denominator, which takes the standard deviation, and divided by the square root of sample size. So after doing this complex calculation, we get our t-score as minus 3.88. Alright, so now we match the calculated statistic against our critical line. So our calculated t-score is minus 3.88 and our boundary is minus 1.833. And you see that it sits deep within the rejection area. Since minus 3 is way lesser than minus 1, that means it will be on the left shaded region. You see, this is the critical value and we received minus 3.88. So it lies in the rejection area, right? So what do we conclude from this? So because our calculated value is way lesser, we reject the null hypothesis again. Let's write down the final contextual takeaway, that there is a strong statistical evidence that at 5% level to suggest that the coffee bags are systematically underfilled and average less than the advertised 250 gram. Alright, so notice how the process mirrors the t-test but requires an extra step up front to calculate your own mean and standard deviation from the raw data set. So always pay attention to the sample details. I hope you guys are now able to run statistical test on single variable and means. Now we are going to pivot to looking at how variables interact with each other. So we'll be talking about correlation. So by definition, correlation is a statistical measure that express the extent to which two variables are linearly related. This means they change together at a constant rate. Alright, so when we talk about correlation, we are describing two things, that is strength and direction of a relationship between the two quantitative variables. But right here on day 1, we must establish the most important rule in data analysis, that correlation does not explain why a relationship exists. It simply highlights a pattern that it is up to us to investigate the deeper to know what is the relationship. So it is just highlighting that yes, there is a relationship. There is no answer to the question that why that relationship exists. To measure this linear relationship mathematically, we use the standard metric called Pearson product moment correlation. Alright, correlation coefficient. So in our sample formulas, we denoted as lowercase r. So there is a beauty of Pearson's R that it is standardized metric. No matter what units are measuring, kilogram, dollar or seconds, the value of R always strictly fall between -1 and +1. So let's memorize the three anchor points for the exam. First is that the value of R, if it is +1, this represents the perfect positive linear relationship. So if you plot this on graph, every single data points fall on a perfect straight line sloping upward. Alright, so you see over here. So this is how the positive correlation means. So here the R is equal to 1. Then we have second kind of where we see that the R is equal to -1. So this is a perfect negative linear relationship. So all the points fall perfectly on a straight line sloping downwards. So this is what negative relationship looks like. Here the R is equal to -1. And then we have the third scenario where the Pearson's R is equal to 0. So this indicates that there is no linear relationship whatsoever. So the scatter plot looks like a completely random cloud of dots. So you can look over here. This is how no correlation looks like. So here the Pearson's R is completely 0. Alright, so mechanically, how is it calculated? So the formula divides the covariance of two variables which tell us if they move together by the product of their own individual standard deviation, which scales the result down to 0 and 1. So it is stated as R is equal to, over here you can see, R is equal to summation of x1 minus x sample mean, y1 minus y mean, and then we divide it by square root of the standard deviation. Alright, standard deviation of x and standard deviation of y. So this is how we calculate the correlation. So we have already discussed about the three main types of correlation. The positive, where the variable x increases and the variable y also increases. That is why we have the correlation positive. In the negative correlation, the variable x increases and variable y decreases. So they move in the opposite direction. So if you see positive correlation, it is an agreeable relationship. So if y increases, if x increases, y also increase. If x drop, y also drop. So a classic example is the education level and the lifetime earning potential. Generally, as years of education go up, the earning also go up. So this is a positive correlation. Next we have negative correlation. This is an inverse relationship. So the variable move in completely opposite direction. So as variable x goes up, the variable y goes down. Alright. So for instance, think of an elevation above a sea level and atmospheric temperature. So the higher you climb on a mountain, the lower the temperature drops. So this is a negative correlation between the mountain and the sea level and the atmospheric temperature. Then we have zero correlation. This means there is no direction or there is no linear pattern. So a change in one variable tells you absolutely nothing about the other. So a great example is zero correlation of Pearson's shoe size and their IQ. So if there is a person A and if the person A's shoe size is 5 and the IQ is 100. So the shoe size has nothing to do with the IQ, right? So the knowing someone has larger foot size, it doesn't mean that they'll have larger IQ. Alright, so it doesn't care about the cognitive ability depending upon your shoe size. So there is zero correlation in such scenario. Alright guys, so if you're tasked with conducting a professional correlation analysis in a project, so you must follow this systematic 6-step workflow. So if you're asked what is correlation, define correlation, explain it in detail, and if it is a bigger marker question, you need to write down this 6-step workflow. So the very first step is define the variables. So you need to identify which are the two quantitative variable you wish to examine, right? Then step 2 is to visualize the data. Always graph your data first using a scatter plot. So never just blindly calculate the Pearson's R. A scatter plot instantly shows you if the relationship looks linear, non-linear, or if it's just completely ruined by a few crazy outliers, right? And then comes the step 3, that is check your assumptions. Ask yourself, are these continuous interval or ratio data? Does it look linear, or are there any extreme outliers, right? And then we move to the step 4, where we compute the coefficient. This is where we run the math manually, or we use software like Excel, Python, or language R to find the exact value of Pearson's R, right? And then we have step 5, where we test for the statistical significance. This is the step students often forget. Just because you get an R is equal to 0.4 doesn't mean that it's real. It could be a random luck as well, right? So you must calculate the p-value for the R. Okay, you must calculate the p-value for the R, and if the p-value is less than 0.05, then you can confidently state that the correlation is statistically significant, right? And then comes the step 6, where we report and contextualize. So finally you write your conclusion documenting the strength, direction, and any potential confounding variable that might be messing with your data or with your variables. Let's talk about one of the most fascinating and dangerous traps in analytics, that is Simpson's paradox. So this is a favorite concept for examiners because it tests whether you truly understand the data segmentation or not. So Simpson's paradox is a striking statistical phenomena where a trend or a correlation appears in several different groups of data. So Simpson paradox occurs when a clear trend or correlation appears in several different subgroup of data, but completely reverses or disappears when those groups are pooled together into a single master set. So if you say these are the group of data and there is some kind of pattern in them, and when we group them, when we convert them into single data set, there is no such pattern. The trend has disappeared completely. That is what Simpson's paradox looks like. It is an illusion of data aggregation. So in terms of correlation, you might look at a combined chart and you see a strong positive correlation. But if you split the data set apart by a hidden third variable, you suddenly discover that every single individual subgroup actually has a strong negative correlation. So let me show you how this happens in real world. Alright, so let's look at this particular correlation. There's an example of exercise versus cholesterol. So let's look at this concrete example. So a study tracking weekly hours spent on exercising, and we regard it as X, and the blood cholesterol level as Y. Alright. So if we view at the aggregated view, if we plot the data of the entire population on one big graph, you see a bewildering positive correlation that if the exercise increases, if the slope goes up, implying that the more people exercise, the higher their cholesterol is. Oh my god, this completely defies medical science, right? This is not. So if we talk about segmented view, however, if we split the identical data by age group, alright, with age group such as people in their 20s, in their 40s, in their 60s, so the picture that emerges now, it is the true picture. So within the people within the 20s group, more exercise correlates with lower cholesterol. Within the 40s group, the scope is also negative. Alright, and within the 60s group, the scope is also negative. Then why did the aggregate graph lie to us? Because age is the confounding variable. So the older individuals 60 plus naturally have the cholesterol level high and may exercise less on average than the 20 to 20-year-old people, right? So when you blindly smash these distinct age groups together, the independent cluster create a misleading upward slope. This is why visualization and segmentation are so vital. I hope you understood the concept of Simpson paradox. So now let's talk about the 8 major correlation caveats. Relying blindly on correlation coefficient without looking at the context will lead to a massive analytical failure, right? So let's look at the major 8 traps that must happen in correlation. So the very first is non-linear relationship. So Pearson's R is designed strictly for straight lines. Alright, so if your data has perfect U-shaped quadratic curve, for example, anxiety versus exam performance, so where your little anxiety helps you focus, but too much anxiety might paralyze you and affect your performance, right? So Pearson's R will be close to 0. It will falsely tell you that there is no relationship, when in reality a very predictable non-linear relationship exists over there, right? So this is falsely implying no existing relationship. This is a caveat, right? And then the second is outliers. So the Pearson's R is highly sensitive to the extreme values. It is highly sensitive to outliers. Alright, so a single value, a single anomaly sitting far away from rest of the data can inflate the weak correlation, or it can take the beautifully tight correlation into complete arbitrate. Alright, so this is why outliers play a very vital role in affecting the correlation. It can make the weak one seem perfectly strong, or it might take the tight correlation and make it seem like a very weak and obsolete correlation, right? And then we have restriction of range. So if you only sample a tiny narrow slice of your population, your correlation will appear much weaker than it actually is. For example, if you study a correlation between SAT scores and college GPA, alright, so but only look at the Ivy League students. So we are only looking at the Ivy League students. So your data will show almost no correlation because you have restricted the range of top tier scores only, right? So you will never get to know the essence of actual population, right? So when we restrict the range, our data is only representing that particular range only. Then comes the confounding variables. So this is the third variable problem. Just because X and Y change together doesn't mean that they are directly connected. There might be a hidden third variable, for example Z, that might be driving both of them simultaneously, creating an illusion that they both are partner, but rather there is a hidden person Z who is driving them forward, right? So this is the major another problem. Then comes the extrapolation errors. This is the mistake of assuming a correlation observed within a certain range will continue forever into unknown territory. So a company's revenue might correlate perfectly with ad spend up to $10,000, let's say, but multiplying that ad spend to rupees dollar of 10 million won't yield the infinite exponential growth due to market saturation, right? So this is the extrapolation error, where we are assuming that a correlation observed within the specific data will continue to an unknown territory, that if we spend more then it will lead to more market growth. That is not how a correlation works, right? Then comes Bergson's paradox. This is a tricky selection bias that happens when your sample pool isn't representative of general public. For instance, if you only gather the data from hospital patients or from university admission, you might find negative correlation between the two completely independent positive traits. Simply because people who lack both the traits are excluded from excluded from your entire sample, right? So this leads to Bergson paradox. So what is happening over here, that people who don't have those independent traits would completely be excluded and your sample would lack that, which would lead to a bias, which would lead to a selection bias, right? Next come to spurious correlation. Okay, so in the age of big data, if you run correlations on millions of random variables, you will find purely coincidental association that are highly statistically significant but completely meaningless. So my favorite example is the historic real world data showing a near perfect correlation between the US spending on the science and space, alright, and suicide by hanging. Okay, so they have nothing to do with each other. It's pure mathematical coincidence, right? That US is spending on science and suicide, right? So this is what is spurious correlation. Then comes the autocorrelation. So this occurs heavily in time series data, alright. Values collected sequentially are often highly correlated with their own past values. For example, today's stock price or today's outdoor temperature is highly dependent on yesterday's temperature. Yes. So this completely violates our assumption of independent data points, which artificially inflate your statistical significance matrices. So this is what autocorrelation means. And these 8 major correlation caveats might cause a rock in your journey of calculating correlation. So you need to make sure that your variables are completely quantitative, they don't have these kind of caveats, and you are performing your Pearson's mathematical calculation and also making sure that you are rechecking it with your p-value. Now that we are comfortable comparing two means using z-test and t-test, we hit a natural roadblock in data analysis. What happens when we have 3 or more groups to compare? To answer this, we have introduced a massive, highly tested tool in data analysis, that is ANOVA. This means analysis of variance. So before we look at a math, let's clear up the classic exam trap that catches many students off guard. Because of the name analysis of variance, it sounds like we are testing whether the variances of datasets are different or not. This is false. The primary purpose of ANOVA is to actually compare the mean of 3 or more independent groups to determine if at least one of them is significantly different from others. So we merely use variance as a clever mathematical trick to get that answer. Alright, so what is doing is the primary purpose is to actually compare means of 3 or more independent groups and to see if at least one of them are significantly different from each other. Alright, so why don't we just use multiple t-test if we have to test multiple problems, right? So a very common conceptual question is this, that if we have 3 groups, why can't we just run a multiple standard t-test? But let's look at why that is a statistical disaster. So imagine you have 3 groups. Imagine you are testing 3 different website layout, group A, group B and group C, to see which generates the most sale. So if you wanted to use t-test, you would run 3 separate comparison. You'll run one comparison for A versus B versus C, A versus C, right? There would be 3 test comparison you would run. So remember our discussion on errors, that every single time you run a t-test, you accept that there is a 5% risk of committing a type 1 error, right? Type 1 error, that is false positive. And if you run these 3 independent tests, your risk doesn't stay at 5%. They accumulate. So mathematically, the probability of not making an error across 3 tests is 0.95 cube, which is approximately 0.857. So this means your actual cumulative risk of making type 1 error has inflated exponentially to 14.3%, and that is very much. And if you had 5 groups to compare, for example, then you would need 10 t-tests, and this would skyrocket your error rate to 40%. So you would be claiming that statistical breakthrough, that it is nothing more than a random luck, right? 40% risk would something means not a good choice at all. That is why ANOVA comes into being. ANOVA solves this problem perfectly by running an omnibus test. Omnibus, it is considering the test at all the different types of samples which we are having. So it evaluates all the groups simultaneously in a single shot, keeping our overall risk only strictly at 5%, where the significance rate is only 0.05. Alright, so that is why we use ANOVA. So first you need to see the core terminology. So to master the numerical problem which we solve by using ANOVA, you absolutely must learn the specific vocabulary, right? So examiners look for the exact terms when grading your step-by-step solution. So make sure that you're noting down the keywords. So the very first is the factor. Alright, so factor is the overarching categorical variable used to separate your data into distinct groups. So it answers the question, what attribute am I changing? Okay, example includes like type of medication, training method, website layout design. So this is the particular factor which is dividing the data into groups. This is the simple thing. Or we can call it as an independent variable which is not dependent on anything. Other variables are dependent on this factor. Then come the levels. Level are the specific individual treatment group or category contained within your factor. Alright, so these factor contains level. Alright, so in our notation we represent number of levels with letter K. Okay, for example, if your factor, that type of diet, this is your factor. Alright, so the level might be, there are keto, first diet, vegan, and then we have Mediterranean. So what are the levels? We have 3 levels. So K is equal to 3. Simple as that. And then we have dependent variable. Dependent variable are the continuous numerical metric you are actually measuring in your experiment. So it is the outcome data. Following your diet example, your dependent variable would be something like total weight loss in kilograms. This might be your dependent variable in this particular example. Alright, let's move on to understand how does ANOVA compare these means by looking at variance. Alright, so let's break down the total variance in your data set. So other thing you need to understand is there is another term, grand mean, which is average of all data points across all the groups. Okay, so that is why it is known as grand mean. And then we have between group variance. This measures how much average of individual group differ from each other. Okay, so what is the average difference of one group with another group? So if our diets are highly effective, the distance between the group average will be large. Okay, so this is the between group variance. What is the variance within the individual groups? And then there is with group variance. Okay, this measures the natural variation or random noise inside each individual group. So how much individual people on the same exact diet differ from one another? Okay, so we are just talking about the within one individual group, but in this we are talking about within one individual group, how many people, how many individual on same diet are different from each other, right? And in between group variance, we are talking about two different individual groups. Okay, and how they differ from each other. I hope you understood this point, right? And lastly, ANOVA divides the two values, the total, it divides the two values of between group variance and within group variance to calculate the matrices called F statistic. Okay, and this is how we achieve the statistics. So think about it logically. If the variance between the group is massive compared to the random noise within the group, your F statistic will be large number. A large F statistic proves that the difference between the group is too stark to be fluke, leading us to the reject of null hypothesis. Alright, so see, if F is close to 1, the groups are practically identical. If F is significantly larger, then the difference among the group mean is larger than the background noise. So this is how we are able to differentiate that particular part. Alright, now we'll talk about what are the core assumptions about ANOVA. So before we dive into the actual mechanics of our numerical problem, we must address the entry conditions. So just like Z-test and T-test, ANOVA has a strict baseline checklist. So if your data violates these three assumptions, your final F statistic cannot be trusted, right? So first comes the normality. A continuous dependent variable must be approximately normally distributed within each individual group. So for our upcoming example, this means customer spending for layout A, layout B and layout C should each form a symmetrical bell curve. Alright, that is the normality. Then comes the homogeneity of variance. Okay, so this is a fancy term that means equal spread. It means equal spread. So the variance inside each treatment group needs to be roughly equal. Okay, variance inside the group needs to be equal. So if group A's range from 4 to 8, group B data swing widely from 0 to 10,000, let's say. So you cannot run a standard ANOVA on this particular data set. Okay, and then comes the independence. So the data point must completely independent within and across group. So one customer spending on layout A cannot influence what another customer sends on layout B, right? This is what independence means. That means observation within and across group must be completely independent of one another. Now let's walk through a comprehensive numerical problem together. So there is a scenario that says that a store manager, so imagine a retail store manager who wants to test if the three different website layout design, layout A, layout B and layout C lead to different average spending amount per customer or not. Alright, so they randomly assign 12 customer to 3 layouts. So 4 customer per group, and here is the raw spending in dollars. Alright, so for layout A, there was 6, 8, 4, 6. These were the spendings. For layout B, we had 8, 12, 9, 11. For layout C, we had 13, 15, 11 and 13 again. Alright, so the very first step to understand is to formulate the hypothesis. So our null hypothesis would state that there is absolutely no difference. That means the group A, layout B and layout C is exactly performing identically. That means the average spanning is same across all the layouts. That is what our null hypothesis state. And the alternative hypothesis would state completely opposite, that at least one of the layout mean is different from others. Okay, so note that it doesn't tell us which one is different yet. We are just assuming that there is a difference that exists. Alright, now we come to the step 2, where we calculate the group mean and the grand mean. So for layout A, we summation of x1 is complete, this row is 21 and then 24, and 24 divided by 4 comes to be the mean of the layout A. Same for layout B, the mean is 10, and for layout C the mean is 30. Now we combine all data to find the grand mean. So now we plus these all. Alright, so what is the grand mean? We get 24 plus 40 plus 52 divide by 12, where we get 9.667. Alright, so our sample size was 12. Alright, and our total were 24, 40 and 52. Alright, so the total is 24 of layout A. For layout B it is 40, and for layout C it is 52. So we divide these by the 12, which is the sample size of people. So we get 9.644. This is the grand mean. Now comes to the step 3. In step 3 we calculate the sum of squares between the group. So this component measures the variance caused entirely by our website changes. So it tracks how much our individual group mean deviate from the overall grand mean. So the formula is summation sample mean, and where we are using the actual mean minus the grand mean, and we are squaring them. Alright, and we do this, we plug this formula for all the groups. So we just put the value where our sample mean of for group A is 4, and then for the value right, so the mean of layout A is 6 minus the grand mean, then 4, and the second mean is 10 for layout B minus the grand mean, and for 13 minus the grand mean. And when we calculate all of this, we get our final value as 98.668. Okay, this is the final value. So this represents the baseline structure variation between a 3 layout. Alright, so this is the sum of square between the group. Then comes the sum of square within the group. So now we need to look at the noise or the natural variance inside each group relative to its own mean. So the formula is summation of x minus the mean, and we are squaring that, and we'll run this calculation on each individual customer column. Alright, so for layout A, our mean of group is 6. So 6 minus 6, 8 minus 6, 4 minus 6, 6 minus 6, and we square them all, and then we finally find the answer. So we are using all the particular value of these row value. Okay, so this is what we are using, the spending, and then we do same for layout B and layout C, and we get our desired answer. After getting the answer, the very next step is to combine them. So to combine the total, so total is combining all of them, and we get 26. After getting the sum of square within, we also have sum of square between, right? So sum of square between, I told you it was 98.6. Now we'll calculate the sum of square total by adding between and within values, which is 98.6 plus 26, and approximately our value would be 124.66. I hope you understood this thing. Next step comes in determining the degree of freedom. After having a value, to convert our crude sum of square value into a usable variance average, okay, we must divide them by their respective degree of freedom. So this is where many students trip up on exam. So follow this simple definition. Alright. So between group, this is the we are calculating sum of square between divided by the degree of freedom between. So what is happening? The degree of freedom between is 2. So you see we have calculated k minus 1. So we have 3 types of groups, right? So it is 3 minus 1 which equal to 2. So this is the degree of freedom. So k is the number of group and we have 3 groups. So k minus 1, 2. Usually it is n minus 1. Here we use k minus 1, right? And then we calculate mean square within. So here we have sum of square within with the degree of freedom within. So what is happening? We calculate n minus k while calculating degree of freedom within. N minus k, where n is our total sample size, which is 12, minus k, which is 3. So there are 3 types of layout, right? So 3, which is equal to 9. So this is how we get the mean square. After getting the mean squares, we actually compute the final F statistic, which is MS between divided by MS within. So mean square between divided by mean square within gives us the value of 17.08. So to finish our exam question, you would compare this 17.08 to look up the critical value in our distribution. So the distribution table of F statistic. So you will see the degree of freedom 2 and 9 at the significance level 0.5. So when you look at that table, go look at yourself the F statistic table, and for the degree of freedom 2 and 9 at 0.05, you will find that the critical value is 4.26. And because our calculated F statistic is 17.18, it is significantly larger than the critical threshold, which is 4.26. So we reject the null hypothesis. So this is a strong statistical evidence to prove that the website layout design result in different average customer spending amount. Alright, so that completes our full step-by-step layout. I know the ANOVA problem is quite difficult bit because it compromises of various different formulas as well, but if you try it few times, you would be able to understand how we are calculating this thing. So we quickly calculated the hypothesis, then the group mean and the grand mean, then we calculate the sum of square between and then sum of square within, and after that mean square between, mean square within, and finally the F statistic. You just need to remember the terminologies and the basic formulas, and you will also have a calculator during your exam. Mostly you have it in your IPU BCA university exam. I don't know about others, but to calculate this kind of question, you are always given a scientific calculator. That makes your calculation very easier since you're not doing it manually. You just need to remember the logic, the conceptual mathematical understanding of the basic concept, right? We have spent a lot of time analyzing patterns and correlations in data, and now we are moving to the goal of data science and analytics, that is causation. So while correlation tells us two things change together, right? But causation is cause and effect. So that means that a change in one variable directly physically responsible of producing change in another variable. So if X variable causes variable Y, then actively manipulating X variable by decreasing it or increasing it will alter the value of Y as well. So in business and technology, finding correlation is nice because it helps us predicting things, right? But finding causation is the real gold mine. Why? Because if you want to actually step in and change an outcome like increasing the sales or reducing the server downtime, you have to pull the lever of the true cause. right? So there are three pillars of proving causation, that is correlation first, right? So correlation is association. So the absolute bare minimum requirement is that a statistical relationship must exist, that the two variable must must change together in a predictable pattern. So if x goes up, then y does absolutely nothing or moves completely at random, then there is no correlation, right? And therefore there cannot be any causation. So causation depends on correlation. Then comes the temporal precedence. All right, so this is a fancy phrase for a single logic rule that the cause must happen before the effect. All right, basically it is a time order thing. So what it is saying, that the cause, the reason should happen before the outcome. So if you claim that x causes y, then you must prove that x change first in time, and then y change as the result of x. Okay, and if y changes before x occur, your causal theory is completely dead. Therefore first there should be correlation, second there should be temporal precedence, and then there should be non-spuriousness. That means ruling out the third variable. This is the hardest pillar to achieve. So the relationship is spurious, means if it looks real but is actually an illusion. So to prove causation, your relationship must be non-spurious. Alright, meaning you have completely ruled out all the hidden confounding third variable. Remember I told you about the caveats, correlation caveats, in which we talk about this, right? So there is an x and y, but there is a z variable that is actually making them partners and moving them forward. So this z variable that might be driving both x and y at the same time should be removed in order to have a causation. So these are the three pillars to prove causation, right? So let's look at a classic textbook example that perfectly illustrate why these three pillars are so critical. So imagine you're analyzing a local health and a retail data for a beach city. Okay, so you plot weekly local ice cream sales. You plot weekly local ice cream sale against weekly hospital visit for the sunburn. So the ice cream sale is x and the sunburn is y. So we let ice cream sale as x and we let sunburn as y. Alright. So when you run the mathematical analysis, you find an incredibly high statistical significant positive correlation. And if we talk about non-spuriousness, this is where the theory falls apart. So the question that does buying an ice cream cone cause your skin to burn? No. Does getting painful sunburn cause biological mutation that makes you crave ice cream? Of course not. So the relationship is completely spurious. Alright, so buying ice cream does not cause skin damage, nor does the sunburn cause sugar cravings. So what is the cause reality? So the relationship is spurious. What is the true driver? There is a hidden third variable, z variable, that is driving both of the things, right? That is the hot sunny summer weather. This is the hidden variable. So when the weather gets hot, it independently causes people to buy ice cream, and it independently causes people to go out, right? Go out without sunscreen, leading to sunburn. So the sunny weather, the hot weather is the true cause. The relationship between ice cream and sunburn is an illusion. I hope you understood this thing, right? So let's move forward and discuss causation versus correlation. So when writing the definitions for your exam, make sure you clearly contrast the two concepts across the core features. First, the definition. You write a detailed definition. I have just given you a simple key pointer, but make sure that you are completely writing both of them. you might also need to write what is the relationship among them as well, right? So the correlation is when x and y change together, and causation is when x makes y happen. All right, so causation means x is leading to y. And if we talk about directionality, correlation is completely symmetrical. So if x correlates with y, then y automatically correlates with x, right? So with the exact same strength. But causation is strictly asymmetrical. If flipping the light switch x causes the light bulb to turn on, then twisting the light bulb does not cause the switch to flip itself. Alright, so this works only one way. It is unidirectional only, right? Then comes to the data requirement. Correlation only requires basic passive observational data only. You just sit back and watch, whereas causation requires rigorous experimental design, like diving people into random test group to control for outside factors as well. So there we require the experimental design, right? And it is used for prediction, it is useful for intervention and policy making. So what is the actual relation among the correlation and causation? So you need to understand that correlation is necessary, but it is not sufficient condition to cause causation. It is not sufficient condition because we have other two pillars as well, right? So necessary means that you must have it. Correlation must exist. You cannot have causation without correlation. Correlation is the starting point, the footprint that tells you that a relationship exists. But it is not sufficient. Not sufficient means that correlation on its own is not enough to close the case. It is only one step. To finalize the proof of causation, you must take that correlation and back it up with temporal precedence and non-spuriousness, right? So keep this boundary line clear in your mind as we move forward, right? So this is what we have wrap up. Please memorize the important keywords, the important parts of statistical testing, and the important terms that governs the statistical testing. Alright guys, this is the end of unit 2. We have successfully discussed the entire conceptual knowledge and mathematical knowledge of unit 2 as well. So you need to understand what is the hypothesis testing, and I hope you are able to analyze about z-test and t-test till now, and you can easily talk about what is correlation and causation, confidence interval, Simpson paradox. And please revise and try the questions yourself. Please memorize the formulas and also understand the conceptual knowledge behind those formulas as well. And if you guys want me to discuss the exact numericals that had been asked previously in the PYQs, please like, share, subscribe to my channel, and also comment down numericals, and I'll share you the video discussing the exact numericals which were asked in the previous year paper. Till then, bye bye, all the best for your exam, and stay tuned.